All right, well, in this section, we're going to start multiplying and dividing rational expressions. And at the very top, though, they just start with asking us to simplify the rational expression. So remember, a rational expression just means we're dealing with fractions. We're either going to have an x term in the numerator or in the denominator or possibly in both. And so that's what makes this why we call it a rational expression. But in order to simplify it, they're really just asking us to reduce it down to its lowest terms, just like you would any other fraction. If you had a fraction 5/10, in order to reduce that or simplify it, you would take the factor of 5 out of the numerator, the factor of 5 out of the denominator, and you would cancel them. And so you would end up, instead of with 5/10, you would have the reduced form of 1/2. That's the same thing we're doing here. So in number one, in order to start that process, since we have a binomial in the numerator, we need to pull out the GCF. So we're going to factor out that 3. And we're just rewriting the expression. So now it looks like this. Same, we didn't change anything. We're just changing the way it looks. But now what that allows us to do is see that we have a 3 in the numerator factor, as well as two threes in the denominator. And so we can cancel the 3 and get 1 here. 3 divided by 3 is 1. 6 divided by 3 is 2. And so we end up with a simplified rational expression that looks like this. Okay, so we just reduced out, we took out the factor that was common to both the numerator and the denominator. In number 3, we would do the same thing. X plus 2, of course, is already factored to its simplest form. And then here we'd have x minus 2 times x minus 2. Now, in this case, there's no GCF between the numerator and denominator. There's nothing that they have in common that could be canceled down. So this right here is in its most simplified form. It's not possible to simplify it further. So we could say simplified. Number 5, we're going to pull the GCF out of the numerator. And then we'll factor the bottom. And now we can see that the x plus 4 is a factor in the numerator as well as in the denominator. So those two cancel down to 1. Right? We're just dividing them out because remember, all these terms are being multiplied together. So we're just reducing the fraction. We're using those properties that say we can reduce the fraction by canceling numerator to denominator as long as it's multiplication. I mean, if we had an addition sign somewhere in between the parentheses and the x, or down here in between these two, we wouldn't be able to do this. All right, and so there's our final answer there. Now, if we move down the sheet, we're going to start actually multiplying the expressions together. And so in this case, we've got everything in the numerator and denominator is being multiplied together. We don't have any addition or subtraction in here. And then we're multiplying the two fractions together as well. So if you go back to the basic rules of multiplying fractions together, if everything is being multiplied together, you can cancel numerator to denominator when you reduce, as well as numerator to denominator in the fractions that are across from each other. Right? The only thing that that you can't do is cancel across like this. And so, of course, there are numerous ways to do this. This would be one. If I divide, I'm going to reduce the 6 and the 8 by dividing by 2. That'll give me 3 there and 4 here. If I reduce the x's, I can reduce my x's this direction. Actually, I could reduce them this direction as well, and that would just get rid of them completely. So x cubed and x cubed will go away. I can do it this way with the other x's. So x squared and x, I'm dividing them. So I'm just rewriting the base and subtracting my exponents. So I'm going to end up with an x of 1 up here. And I'm just going to leave the y's alone here, just so I don't have to deal with negative exponents. I mean, here I would end up with a -1 on that as an exponent, which it will work out. But honestly, I think it's probably just easier to go ahead and multiply the numerators together. Now, like say that the reducing is done, the canceling, go ahead and multiply my numerators together. 3 times 3 is 9, and then I have that x and that y left over. Actually, that should be y squared. I have a y in both terms. And then in the denominator, I'll end up with that 4y squared. And now I can see really easily that my y's are just going to cancel out completely. So I'm going to always double check at the very end that I don't have any more canceling, any more reducing that needs to be done. And then so we'll end up with 9/4 x. We could call it 9x over 4 or 9/4 x. Either way will work. And that's completely reduced. All right, we'll do the same thing on number 8. I'm going to start by trying to simplify my constants. So I can divide 44 by 22 and get to, and 22 divided by 22 is 1. That's all that I can do with my constants. So then I'm going to move to my x's. I have an x to the 7th here and just an x to the first power here. So I can subtract those exponents, 7 minus 1. This one will go away completely, and instead of having an exponent of 6 here, I'm going to have an exponent of, exponent of 7, it'll go down to 6. My y's, my y to the 4th right here, minus this squared, so 4 minus 2, this one will go away completely, and that'll be a 2. So I'm going to end up the y squared there. Now I can also see, before I go to do my final multiplication, I have an x to the 6th in the numerator here and an x to the 5th over here. So I can cancel these out. The x to the 5th will go away completely. The x will just become an x to the 1st instead. Okay, so instead of x to the 7th, now we have x to the 1st. Right, and then there are some other things I could do with the y's, but I'm just going to go ahead and leave that alone and do my multiplication, do my final reduction at the end. So 2 times 12 is 24. I have an x and an x, so we're multiplying them together, rewrite the base, add the exponents, and then y squared and y to the 5th, rewrite the base, add the exponents. And all of that is going to be over 5y cubed is the only thing I have left in the denominator. My constants look good. There's no reduction there. I don't have an x squared or an x term in the bottom, so I'm done with that. My y's can still be canceled. And so if I divide those out, that would be y 7 minus 3, y to the 4th, and all of that is going to then be over 5. Right, now if we move to the back of the worksheet, we're going to try one division problem. The fractions work the same when they're rational expressions as they do when they're just constants. And so if we're going to divide fractions, we know that we actually have to multiply the reciprocal of the second term. So that's all we have to do here is just put a multiplication sign in there and reciprocate that second fraction. And now the rules are exactly the same as they are for other fractions. So yeah, let me change colors here so we can see that better. I'm going to reduce my constants first. So I'm going to go and divide this out by 2 and this one by 2 as well. And then at that point I'm done with my constants. I'm going to move to my x's. My x to the 4th here is going to cancel with this x down here. So I have 4 in the numerator, 1 in the denominator. That one will go away, and this will give me an exponent of 3 here. I can see that if I want to go ahead and take care of these x's, my x cubed here will cancel with this x squared over here. So I've got 2 in the denominator here, and I have 3 up here. So I can just get rid of that exponent. I'm only going to have 1 left in the numerator. And then I have my y's. So my y to the fourth here will cancel with this y. This one will go away completely. This will leave me with 3 in the numerator. And then actually I can still do some more, canceling pretty easily with these y's. Y to the third here, y squared here. So we've got 2 in this denominator that will go away and leave me with just 1 y in this numerator up here. All right, so that was a lot of canceling fairly easily and simply. Now I can multiply my numerators, 5, and then I have 2 x's, so I'm going to rewrite the base, add the exponents. I've got that 1 y, and then only thing left in the denominators are those 2 constants, 3 times 3. And so this will be my final answer for number 13. All right, number 19. Great SAT-like question. They are combining geometry and algebra 2 here, and so this is a good question to go over. In the diagrams below, the length of the edge of the square is twice as long as the radius of the circle. So we'll get back to this. This is an important piece of information to know for the very end when we have to actually solve for this. They say to find the ratio. That's an important word right there, because we know ratio means a fraction, one thing over another, a proportion. We're comparing the two. Find the ratio of the area of the circle. So there's a formula we need to know to the area of the square. So we're going to start by setting that ratio up. And so if they've asked us, I'm just going to write it out in words first, just because sometimes that makes things a little clearer. We're going to put the area of the circle over the area of the square. All right, seems like the most obvious place to start. On these kinds of word problems where it looks a little confusing at the beginning, just start with what you already know. Just start with what you know to do. And we know what a ratio is, and we know that that means we're going to set these two over each other. So just write out in words can help at the beginning. Now I can focus on remembering the formulas. So my area of a circle is pi r squared. So I'm going to write that over the area of a square. Now, and we know the area of the square is the length times the width. In this case, we've got our length here, and we have our width here. And so if we multiply the two of those together, since they gave them the variable of x, then I can just write x squared. Okay, so now we have our ratio set up, but we still know we have way too many variables going on here to really actually be able to solve anything. And so that's when I'm going to go back up and look at what they told me. They gave me that extra piece of information at the very beginning that said that the length of the edge of the square is twice as long as the radius of the circle. So the length of the edge of this square is twice the length of this r right here. And so if we put that into our an expression, then what we would have is this length x equals 2 of these r. All right, so x equals 2r. You could also have r equals x over 2, or 1/2 x. This one is a little bit easier to deal with because we don't have a fraction then. So now I can actually substitute that in for my x squared down here. So pi r squared and 2r squared. All right, so I'm subbing it in. This is just x, so I've got to make sure that I actually square it. Okay, and now we have the ability, we only have that one variable, so now we have the ability to actually solve, to simplify it, which is what they asked us at the very end. They said simplify it. So in order to get it down to an answer that's maybe going to match something that we could choose from, we're going to need to simplify. All right, so I just squared. Make sure you square both the 2 and the r. And now these r squareds are going to cancel out, right? Because we've got multiplication is the only thing happening here, so we can cancel r squared with r squared. Or you can think of it as rewriting the base and subtracting the exponents. 2 minus 2 gives me 0. So r to the 0 is just 1. And then we end up with pi over 4. So the answer to their final question to find the ratio of the area of this circle to the area of the square is pi over 4.